think. So it was the linear model. The non-linear SVM is what we have not seen, I remember. Is that so, Sahaswat?
Yes, ma'am.
Okay. So I had shared a Python notebook where the non-linear model was also available. Example was also available. Can one of you share your screen? Can one of you share your screen? Is that available with you guys? You have it or not?
Just a moment, ma'am. I'm looking at the files. If I find it, I'll immediately share, ma'am.
Yeah.
Ma'am, is it the code which is expected, ma'am?
Yeah, actually, yes.
Yes, ma'am. Just a second. Ma'am, can I share my screen, ma'am?
Yeah, please share your screen.
Yes, ma'am. So, this was the SVM's of code which is done, ma'am.
Okay, so we have done the linear model. If I have to quickly summarize, classification is the aim of SVM, and then the two groups of data points, in order to separate them, we are drawing two margins first before we draw the central hyperplane that separates the two groups. So the margins are drawn in such a way that you have each margin at the last point of a group. So at the boundary of each group. So you have two margins, and the central line is supposed to be the classified boundary plane. So we have this SVM. Now, some of the terms, I think, if I'm not sure, we have discussed that. See, there are a few things which is common to not just SVM alone, it is common to the other machine learning models also. Now, how best can you get the margin or the central hyperplane depends on the data set. Which group of people are we talking about, or which group of data points we are talking about? Depending on that only we are training this hyperplane. So another new data point when it comes in, we need to check whether it falls into one of the group. The central hyperplane that we have trained, is it able to clearly distinguish which group it is going, and is it doing it correctly? So this is testing. And then for testing also, we can have, for example, 100 data points. When we have, usually 70-30 is divided for training and testing. So this within the same group itself, one big portion we use for training and a small portion we use for testing the designed hyperplane. Now any new data point other than this whole set, we actually don't know whether it belongs to this group or not, or which group it belongs to. So that is when you can actually evaluate the model we have. Now, that is one aspect. The other aspect is whether the model is there a trade-off in the model in terms of accuracy or in terms of uh, how good is the model? Has it completely learned the given data set? If it has completely learned the good data set, I mean given data set, then for a new data point it may not be able to understand. So this is something like, if you completely understand the a particular country, people of a particular country, maybe for example, Myanmar, or take a small country, so let's say Indonesia. You have understood. So when you have another person coming in, whether he belongs to Indonesia or not, finding that out depends on how well you have understood the Indonesian country people. Same way, given a data set, so this may look like if you learn all the characteristics of the data set perfectly, then any new data point, whether it belongs to this data set or not, you will be able to identify. But that's not how it is. We have to understand the general characteristics. If you go very deep into every person's, features and characters and characteristics and the mannerisms and go and so on, if you go deeper, you won't be able to identify something common among the entire group. Therefore, there should be a trade-off. You have to have some kind of generic idea about the whole data set in order to understand for a new data point whether it belongs to this data set or not. So this is called generalization. When you do generalization, you may actually lose some amount of accuracy. So this is actually a trade-off. So if you don't generalize a given machine learning model to the given data set, if you don't generalize, or if you, what do you mean by generalization is the general characteristics of the data set. If you don't model it, then your model will not be able to work for data points outside this group. In the sense, somebody you have not seen before, but he actually belongs to this data set. When you look at him, the general characteristics, if you identify only, you can say he belongs to this data set. Otherwise, it is difficult. That's the reason why generalization is very important in a machine learning model. So how do you identify whether generalization is there or not in your model? Whether you have actually generalized the model or not? How do you identify that? We reduce, when we do the training, as much as possible we try to classify the two groups of data points exactly, in the sense all data points are clearly put into any one of the groups. That is the best training model that we can have. But it's also possible that for a given data set, depending on the distribution of the data points, let's say you have red data points and blue data points. Now if these are overlapping, or it's a mix, it is spread, both of them are spread equally, then it is very difficult to actually put a line between them. How is that possible? No, it is possible. Something must be different between the two. That is why they belong to two different groups. So what is that something? So a generic idea in SVM is to put it in a higher dimension, putting all these points in a higher dimension. In the next dimension, maybe. So the current dimension we are looking at is the two-dimensional model. So if we go to a higher dimensional model, maybe the blue points rise up and the red points, keep low. So in the third dimension, maybe they are differentiable, I mean they are discriminatable. So that's the reason why SVM actually works on, SVM allows it. So that you call it as a non-linear model. The reason it is non-linear is you will not be having a straight line or a simple plane to separate the two. So here it is a straight line. In two-dimensional model, the plane that you're calling, the central line, is actually the separating boundary plane. Now it's in two-dimensional model, it is is a linear model. When you go to higher dimensions, then you will have a higher dimensional plane or object that is used to separate the two groups of points. So that's what we are interested in looking at. Now, as we go by, we should also learn another term. When we try to reduce the error while training, gradient descent is one aspect. Did we discuss about gradient descent before? We did discuss, right? During linear regression, we have discussed about gradient descent, is it not? Guys, are you there?
Yes, ma'am.
Gradient descent is simply, reducing the error. So it is actually, as you keep reducing, so how do we reduce the error? Every iteration, it's like machine learning. The fundamental idea is you first assume where the margins are and then you start aligning them correctly. So this happens through from the code itself. This happens. You calculate the error first. For your first assumption, what is the error you calculate? In order to reduce the error, how do you orient the margins, change a little bit, and then see the error. If it is lesser, you know that you're going in the right direction. The orientation of the margin can actually move in the same direction in which you moved right now. So for the next iteration, move in the same direction a little more and calculate the error. So likewise, you can see the error going down, down, down. So it is gradient descent. Now, the point here is, when you want to generalize the model, sometimes you may not go for zero error. In the sense, the least error you may not go during generalization. So in order to change this orientation, or even in linear regression, changing the weight parameters, as the change in weight parameters, you can use some additional parameters to actually reduce the interval of change. For example, delta W might be the weight change. Delta W might be the orientation change in SVM. So instead of saying +1, +2, or +0.1 and +0.2, you can use an additional parameter to actually quantify smaller some kind of adjustment on how much you are doing the change. You call that as regularization. Regularization helps you to generalize the model better. Actually, you have more. So this is like, you have additional screws to actually tighten or loosen a particular object. The same way, regularization helps you with additional parameters to adjust the weight change or the orientation change we are talking about in the machine learning model. So when you do regularization, you will be more perfect in tuning the model to the given data set as well as generalizing the model. So nonlinear SVM is about choosing a specific function that will help us model these margins. You call that as a kernel function. Now that kernel function will be a higher dimensional kernel function. Using a small trick, actually, the higher dimensional function need not be it need not be calculated in higher dimension itself. See, your calculations in 2 dimensions are different. Your calculations in 3 dimensions are different. 4 dimensions are different. When you look at a vector, for example, so let us recollect the basics first. Imagine this Euclidean space where you have a vector and you project the vector onto the x-axis or the y-axis. So when you project it on x-axis, it becomes one dimensional. When you project it on y-axis, the projection becomes one dimensional. Likewise, in higher dimensions, you introduce the kernel but use the projection so that you still work in the lower dimension. For example, you can go to 3 dimension, but you can still work in 2 dimension to get the same effect if you work on the projections. So that idea, you call it as the kernel trick in SVM. Now the kernel trick, it is simply used, whether you use it or not, we are looking at a 3-dimension as the higher dimension for 2-dimension, right? 3-dimension or 4-dimension or 5-dimension. That depends on the complexity of the data set. So just for 2 groups, you're drawing one line, and if the data set is simple enough, we just need to go to the 3rd dimension. And then in the 3rd dimension, we will be able to separate both the groups of data set. So that example we could see here. So I could, you can unshare the screen, Shibi.
Okay, ma'am.
So as you look at this example, we had shared this example in the chat window before. jakevdp.github.io. You can check the chat window earlier. You can see here, this is what we are talking about. So you have these yellow data points and the red data points. Using a straight line, we will not be able to separate both the data points as 2 different groups. Now, if you put them, it's possible to do it with a circle like this. Now, circle is a non-linear kernel. So you have a different kernel function, it's a non-linear kernel. So what you can do is put it in a higher dimension and use a non-linear kernel. Then you will be able to get a circle like this as a separating plane between the 2 groups of data points. If you look at the idea, that's one point. Even in this idea, the margins, the data points in each group that help you draw the margins, align the margins, you call them as support vectors. So we have seen in our last lab session on SVM how to identify which are the support vectors. We have seen that example. Same way, here also you can see support vectors. So you have a margin circle, these dotted lines. You have a margin smaller circle against dotted lines, and then you have a solid circle which is the hyperplane, the separating hyperplane. The decision boundary, you should call this as the decision boundary. So here also you have support vectors which are on the margin. So those data points through which the margin passes through, you call them as the support vectors. So you have 5 support vectors for the red group and 2 support vectors for the yellow group. So is it possible that you can try this example as the non-linear? Now, how do you tune the margins? So this is about tuning the SVM, and how do you orient the margins, adjusting them for a given data set. So can we try this example? And the final example they've shown is face recognition using support vector machines. So before we start exploring this example, face recognition kind of problems, the data set is faces. Actually, the faces with its features are the data set, are the data points. Now these data points, you separate them into 2 groups. So it is like, let's say you have photo of one of your classmates, different photos of the same boy, and different photos of another classmate put together as a data set. You can use support vector machines to separate the features of these 2. So that is one way of classifying the faces. Another one is, whether it belongs to the data set or not using support vector machines. And if we have to, one more point I would like to add is, what is the performance of support vector machines? All of you know that deep learning and other models, machine learning models, deep learning models, and other models are so powerful that they have surpassed the performance of other machine learning models. But only challenge is they need a lot of data set. But support vector machines, they have been, what to say, it depends on the complexity of the data set. Support vector machines have been competing with deep learning models also. Depending on the data set only, you can choose whether it is support vector machines or deep learning. If support vector machines are able to do the job, you don't have to go for deep learning. So with this introduction to nonlinear kernels, we will see in the next theory class, we will look at what you mean by a nonlinear kernel and an example. I will write on my board, digital board, and show you. So this time you can explore this example. Could you do that? You want me to share this link again, or you already have this link? So in the third dimension, as you see here, the yellow points and the red points, though they are in a circle, now they have been separated in the third dimension so that you can have a plane in between. Now, if you project it in 2 dimensions, you will be having a circle. Margin as the circle and the decision boundary as a circle. So this is in 2 dimension, but in the third dimension it is in space and you can have a plane. Working in 3 dimension is computationally intensive, but the kernel trick allows us to work as if we are only in the second dimension, lower dimensions. So please try this example. Beyond linear boundaries, kernel SVM. So this is where you should start generating samples. So you generate samples like this and use the SVM, linear SVM. This is what you will get. You are not able to separate the red points as well as the yellow points. So it's not possible to clearly discriminate the two groups of data points. Therefore, you have to put them in a higher dimension using a nonlinear kernel. And then, the plot for 3D is also available with matplotlib. You can visualize the data set. And then using the, nonlinear kernels, the example used here is radial basis function kernel. So we will look into the details of what kind of functions are available for nonlinear kernels. So here the example they have used is radial basis function. So using this, they are able to get the margins as well as the decision boundary for. Now adjusting the margins for a data set, something like this. So they have, how do you tune the parameters for adjusting and then looking at the face recognition. Please run this example. You can start doing it. So if you can complete this quickly, we can move on to the next machine learning model. Guys, I hope you have completed that exercise. We cannot, go on and on with that. The example is given to you. Is it working? Have you tried? Suraj,
Yes, ma'am.
is it running? It's working?
Yes, ma'am.
Any questions in this, please?
No, ma'am. For now.
Nitish, you have any questions on this? Is it working? Kaushik?
Yes, ma'am, I have a small doubt. How does this kernel trick work?
Okay, theoretically, how it works, we will do it in a class. Okay, at the implementation level only, let that part, we will work it out because we need to really look at the function, what is the input, how it works. So the details of the function are to be written down. So we will discuss in a theory class. Is that okay?
Okay, ma'am.
Yeah. Anybody else? Ashwin, Danya, Anjali, Harihara, Sudan.
Yes, ma'am, it's working, ma'am.
Okay, so we will move on to the next classification model, new type. So let's look at this example. You're able to see my screen?
Yes, ma'am.
Okay, so you can see, around some red and green points. I hope you're able to, yes. So we are going to look at another classification model. This is a very interesting classification model. Basically, this is very, very interesting. So let us try to really understand what this model is. Looking at the data points here, you can see that the red points are on the left and green points are on the right, and there is no space between the two data points. So if we have to use an SVM model, we will have to use a nonlinear model. You cannot use a linear model because there is no space in between. So you have to put it into a higher dimension to create that space, and then a discrimination space, and then we have to create the margins, nonlinear kernel. So there is another way of doing it. So let's say totally there are 60 data points here. The basic idea is very simple. Let's see. The total set of data points here is 60 data points. Out of this, it is red color is 20, green color is 40. So if you bring in an additional data point, what is the chance that it will be red or green? Which is having a higher chance? Because there are 40 green points, we can expect that the new one could also be a green point. Only few red points are there, only half the green points. So the new new point with a high chance that it will be a green point. So this understanding, you call it as, by looking at the given data set. This kind of, faith or belief, let's say for in a given shop, let's say a grocery shop. This morning, around 100 people came to that shop, let's say, and all of them bought milk as well as bread. Milk, bread, and some other item. Out of the 100 people, around 90 people bought milk and sugar. The third item they did not buy, or some many people bought and things like that. But 90 people bought milk and bread. So let us say the 101st person is entering the shop. What do you think the shopkeeper will expect him to buy? Naturally, the shopkeeper will expect the person to ask for milk and bread. After that, only the other items. So he might say, okay, well, what could he, I mean, he might be curious to know what else he wants. But milk and bread, he will be confident that it is highly possible that he is going to ask for milk and bread. Is it not? By observing the data, some kind of understanding you will get. And then that kind of belief, okay, I believe that this is what is going to happen. That kind of belief, you call it as prior probability. This is dependent on the experience that you get till now. So 100 customers came to the shop, and that gave you the experience that every customer now, at this current point of time, the next customer also might ask for milk and bread. So in this case, the percentage of green and red, they are used to predict the outcomes before they actually happen. That is your prior probability. So the number of people who asked for milk and bread and who did not ask for milk and bread, that is how you quantify your experience. Is this clear? This is a very simple calculation. Based on, so quantifying the experience in just in terms of numbers, and then you say that's your probability. So what is the probability that the new point that is going to be introduced, new data point that's going to come in, will be green and will be red? So green means it is 40 by 60, red means it is 20 by 60. So according to prior probability or prior experience that we see right now, what has already happened is the 40 green points and 20 red points. So this is your this is your experience, and from this, the prior or the belief, your understanding, that is called your prior probability. Since there are 60 data points, our prior probability, now you can write like this, as I said, the number of green objects by total number of green objects. Prior probability of green, prior probability of red. So actually 40 by 60 is higher than 20 by 60. So having formulated this, we will also look at another perspective. From another perspective, let us see. So assume that the new data point has come in, and you are going to place the data point somewhere here. Once you place the data point, you are still to identify whether it is green or red. Look at the vicinity of the new point X. If the vicinity is completely green, in the sense, if you keep the point, the new data point that comes in appears in the middle of the green group, the neighborhood of the data point would be completely green. Therefore, you can expect that it is green. If it is in the middle of red points, you can expect that it is a red point, unlike your prior probability. Any new data point, your expectation is that it will be mostly green. The probability that it will be green is higher than the probability that it will be red. That is your prior probability. But once the data point appears and you look at the neighborhood, then it is no longer prior probability. So look at this. So to measure what could be the data point. So let's say the data point is here. Look at the neighborhood. There are 3 red points and 1 green point. So this, what is the chance that it will be red or green? It is more likely that it belongs to a particular color depending on the neighborhood points. So to measure this, you draw this neighborhood, you define the neighborhood, calculate the number of points in this neighborhood belonging to each category. This is called as likelihood. So before even the new data point appears, what is it that you're believing? It will be green mostly. Now once it appears, look at the neighborhood. So this is called as likelihood. the likelihood of X, what you see here in this example, the likelihood of this one being red is number of red in the vicinity divided by total number of red. The likelihood of this being green is number of green divided by the total number of green. This is a totally different calculation. Our prior probability is number of green by total number of objects, number of red by total number of objects. But here in this case, number of red in the neighborhood divided by total number of red. That is the likelihood of red. For green, likelihood of green means number of green points in the neighborhood divided by the total number of green points. So in that sense, there's only one green in the neighborhood, but there are 3 reds in the neighborhood. Therefore, it's the likelihood says that it could be red. Prior probability says that it could be green. So there is a new machine learning model you called as the Bayesian rule. Using the Bayesian rule, naive Bayes classifier model. So the Bayesian rule will combine both prior probability as well as likelihood. Combining both, it creates a point belongs to red or green. So the prior
Ma'am, your voice is breaking.
Yeah, I think I got reconnected. So the prior probability says that according to the Bayesian rule, prior probability of green you have to calculate separately, red you have to calculate separately. So, sorry, the posterior probability. Posterior probability of green is given by, this is Bayes rule. Prior probability of green into likelihood of green. So this is 40 by 60 into 1 by 40. 1 by 40 is 1 green divided by total number of green objects. Now posterior probability of red. Prior probability of red is actually 20 by 60, but likelihood of red is 3 by 20. So multiplying the prior and likelihood, you get the posterior. Now with this, which one is higher? Which probability, posterior probability of green is higher or posterior probability of red is higher? If you look at it, 40 by 60 into 1 by 40 is simply 1 by 60. 20 by 60 into 3 by 20 is 3 by 60. 1 by 60 and 3 by 60. Naturally, the posterior probability of red is higher. Therefore, the new point is classified as red, since that membership has got the highest or largest posterior probability. Is this calculation understood? This is called your Bayes rule, and this is your Bayesian classification. Now,
Ma'am, how is the radius being chosen?
you see that depends on the data set. The radius could be, see, yeah, it totally depends on the data set, and that is where the training happens. Here there is no decision boundary if you look at it. Okay, so the training happens for the neighborhood distance. You may take 1 hop distance, you may take 2 hop distance, or a distance of so many intervals. For example, around 10 points could be your neighborhood. Larger the neighborhood, your probability will become more and more random. It has to be a close neighborhood. So how do you understand the Bayesian rule? For example, how do you understand the Bayesian rule? Okay, so Bayesian rule actually works based on, likelihood and randomness. What is the difference between randomness of an event as well as likelihood? Let's say, it actually quantifies the likelihood, this neighborhood. The Bayesian rule only decides that. So if you flip a coin, it could be red or tail. It could be anything. You know that very well. But if you ask what is the likelihood, then you should say that 50-50 chances for both. That is your likelihood. So actually, how do you say that? How do you say that head has got 50% chance and tail has got 50% chance? Either this or that. How do you say that? What do you understand about that? How do you decide? See, this basic understanding is important for us to use a Bayesian classifier. This is about probability, right? What is the probability of getting a head when you flip a coin? What is the probability of getting a tail? We know that it is 50% for both. How did you decide on that? Anybody can answer this question?
Ma'am, we know that there are two sides and chance of occurring of tail is exactly half, same as chance of occurring of tails. In order to prove it, then they would have conducted experiments like infinite times, and they might have got approximation to that value.
Okay, let me put the question this way. See, you are flipping the coin only once. You are going to get only one of them. And you are saying 50% chance. How did you calculate this 50% is my question. Is it possible to calculate that it is 50%? See, the same coin you're going to flip, I'm going to flip, someone else is going to flip. All of them are going to flip. You're saying that for every person, whenever he's going to flip a coin, the chances head or tail 50%. How did you come up with that? Okay, so let me
Create a
answer this.
sample space and then analyze the probability for each outcome.
Okay, so that is more theoretical, but practically, how do you decide? How do you measure? How do you calculate or how do you quantify this chance as 50%?
And we can say that it's a random event, and so only two sides are available. So 50% chance is the maximum chance of the two, minimum chance of the two sides to be occur, ma'am. Like 50-50 only.
Okay, so when you say a random event, what do you mean by a random event is that you cannot
Uh,
decide what event will happen. That's why you call it as a random event. So here in
yes,
this
ma'am.
case, getting a head is a event, getting a tail is an event. Both of them are called random because when you flip a coin, you don't know whether you will get head or tail. That you don't know. You can't exactly say, okay, this time I'm only going to get head. That is not true. You can never say that. But you can say something. 100 times if I flip the coin, 50 times could be head and 50 times could be tail. That's what you mean by a randomness. Randomness is not like how we understand in terms of English literature. Randomness in mathematics says that you have a equal likelihood for all of them. That's why you call it as randomness. All the events which are considered right now, all of them have equal probability. That's when you call it as a random event. It could be any one of them. That is what you mean by randomness in terms of probability. Therefore, when you flip a coin 100 times or 200 times, 100 times it is head and 100 times it is tail, they have actually experimented and seen. They have actually experimented and seen. You just flip the coin twice. You cannot say that first time it will be head, next time it will definitely be tail. You can't say that. It could be head again. But then over a period of time, it is found that heads and tails, they appear 50-50 times, or half the time it is head and half the time it is tail. That is what you mean by a fair, unbiased coin. That's what you mean by this assumption of fairness is why it is called a random event. That's what is called as a random event. Why it is called random, once again I repeat, is whatever events they are being considered currently, any of them can happen. There is no partial or speciality to any one of the event. Therefore, it is called a random. Therefore, it is called a random experiment or a random, random event. Any one of them can happen. That's what you mean by. So they are equally likely. So if you roll a dice, all the 6 sides of the dice are equally likely. So if you look at it, the probability of head and tail, let's say you have a dice and a coin thrown. What is the probability of a head and a 4? So the joint probability of head and 4 is individual probabilities of head and 4. The reason is these two are two independent events. One is not influencing the other. So probability of head is 1/2. Probability of 4 is 1/6. Therefore, both of them occurring together is 1/12. This is what is actually your samples. If you look at the sample space, what are all the events? Sample space contains what are all the possible events. Probability says that it's a random experiment, means all of them can occur. Any one of them can occur. You cannot predict which one will occur at this point. For a sample space of coin, these two, head and tail. For dice, all the 6 and independent. So this with this background, your Bayesian rule, the Bayes theorem says that if two events A and B, if we know the probability of B given A and the probability of B on its own, you can calculate the probability of B given A. See, you look at this, sorry, A given B. Probability of A given B, in the sense, there are two events A and B. One is the coin flipping, the other one is dice. So let us say the dice is thrown, which is event B. Coin flipping is event A. Now the coin flipping event, given that the dice is thrown, can be treated as probability of B given A into probability of A divided by probability of B. This is the Bayes theorem, and the naive Bayes classifier uses this formula actually. So how is it using it? We will be seeing, right? We'll be looking at it. Again, there's one more term you need to understand. These two are independent events. Since they are not dependent on each other, you call this is a joint event also. So you have two events happening together, but each event is not dependent on each other. You call this actually one of the events alone. When you consider it is called marginal probability. So P of head is marginal probability. P of 4 is marginal probability. When these two events are independent, you just need to multiply the marginal probabilities of the events. It could be more than 2 events, and all of them are independent, means simply multiply their individual marginal probabilities. So now looking at this in that sense, P of A is marginal probability, P of B is marginal probability, whereas once one event is occurring, what is the probability of the other event? In case there is any dependency. In that case, it is P of A given B is equal to P of B given A into P of A divided by P of B. So this P of A given B is a conditional probability which says what is the likelihood that event A will occur given event B. So your neighborhood is B. Once you have understood the neighborhood, what is the probability of A? So probability of B given A is also conditional probability, and P of A and P of B are marginal probabilities. Now having understood this, you should have probability of B should not be 0. Only then this theorem is valid. So we looked at this example. Now based on this, so what is the this P of A given B? This is another example of lone default that I think is we will look at the naive Bayes classifier. How does the naive Bayes classifier work? So let's take an example, the iris data set, which is a standard data set. You have got three different types of flowers. Their petal features are different. So the iris data set, flower data set, consists of physical parameters of 3 species of flower: versicolor, setosa, and virginica. The numbers or the features of this data set are the petal width, length, sepal width and length, and the data consists of numerical values which describe the dimensions of the respective features. So a naive Bayes classifier would consider all of these properties. So we are going to use a naive Bayes classifier. Based on the given features, you have to separate out the two different types of flowers. So what is the assumption that you will have if you have to use the Bayes classifier? The assumption is that the petal length is independent, in the sense you have different okay, and it is equally contributing feature for the classification. So let us just take one assumption that we can have, then we can expand further. We assume that petal length is an independent feature, it is not dependent on anything else, and it is a contributing feature for classification, or this can be used for classification. Look at the three flower pictures. The petal length is different for all the three, and that can be used for classifying. So let's just take only petal length. If the petal length, the range is in centimeter, 1 centimeter to 2 centimeter means the flower type is setosa. 3 to 5 centimeter is versicolor. 5 to 7 centimeter is virginica. So we looking at this classification, naive Bayesian model, what we need to actually, again, just like SVM, from scikit-learn library, we can just call the naive Bayes library, naive Bayes function. data set, also iris data set is available by default. You separate the training and test set, build the classifier and test the output. So how do you build the classifier? From scikit-learn.navebase, import Gaussian navebase, classifier is equal to Gaussian navebase, classifier.fit. So do the training, x-train and y-train. Prediction, classifier.predict x.test. The prediction is y-predict. Summary of the predictions made by the classifier, classification report as well as the confusion matrix. What is the accuracy? Now running all of this on the iris dataset will help you classify. So this is the idea. We can try this example in the next session, next class basically, but I can just share this link with you. Naive-Bayes classifier. The example is fine. We are going to just look at one data point, the red and green that we saw. Here it is red, green and blue, let us say. And they only talk about petal length, nothing else. So one feature you're taking and then using that for calculating the probabilities, prior probability and likelihood you will calculate. Calculate the posterior probability for versicolor separately, virginica separately and setosa separately. So the posterior probability of all the three categories, once you get, you know which is have the new data point, the testing, the prediction, actually testing the model. The new data point, whether it belongs to any one of these categories, which category, which type of flower it is. So the classifier will be able to help you do it. So getting into the mathematics with individual features, and we will learn the model, how the training is done. So the naive-Bayes model as well as the kernel function of SVM. So these are the two things we will discuss in the next class. We will stop for today because, and actually you can, I've shared this link, you can try the naive-Bayes example for iris data set. This you can try, but the theory, we will go into it in the next class. Any questions? Guys, you have any questions?
No, ma'am.
No, ma'am.
Okay, so we'll continue. I will let you know the Viva date. Okay, thank you guys.
Thank you.
Thank you, ma'am.
Thank
Thank
you.
you.
Thank you, ma'am.
Thank you, ma'am.